Chapter 7, the final chapter of the semester. So in this chapter, it has applications of trigonometry and vectors. So we're doing the vectors in the later sections. In this first section, 7.1, we want to, basically we want to begin to learn how to solve a bunch of triangles that are not right triangles. And so let me describe what that means as an intro to chapter 7 to motivate what we're going to do. So if I have a nice right triangle, and I told you, for example, two of the sides of the right triangle, like this is 3 and this is 4, then you could use the Pythagorean theorem to find out that this is 5. And if you wanted to know the angles in here, you could, for example, say, all right, to find this angle theta, I know sine of theta is equal to opposite over hypotenuse, which would be 4/5. And then I could figure out that theta, because it's an acute angle, would be the inverse sine of 4/5. And I could get that angle. That's the exact value. I could type that on a calculator and get that accurate to whatever level I need it. So finding out in a triangle the parts you don't know using the parts you do know, as we've done in the past with right triangles, is called solving the triangle. So what we want to get able to do now is to try to solve triangles that are not right triangles. Solving triangles that are not right triangles. And there's going to be a couple of different methods we use to do that. We're going to look at that in 7.1 and in 7.2. And we're going to learn some new tools, like there's something called the law of sines. And then in another next coming section, we'll learn the law of cosines as well, in order to help us figure out how to solve triangles. And the reason we want to solve triangles is because if you can find out the missing parts of a triangle, missing angles, missing sides, things like that, you can solve all kinds of real world problems. And so there'll be quite a few application problems that we're doing along the way as well, where there's some triangle in the real world and we want to find the length between 2 points of a missing side, things like that. Anyway, so that's what's going on in general. Let's see how we proceed down this. We begin by introducing some notation, some terms, and some ideas. So the first thing here is SAS, which stands for side angle side. So this describes a situation for a triangle in which we know two sides and the angle between them. If we have two sides and the included angle of one triangle, if those turn out to be equal, respectively to two sides and the included angle of another triangle, then the triangles are congruent. So what does that mean? Congruent means the triangles are the exact same triangles. Means that all angles are the same and all side lengths are the same. So if I have a triangle over here, and I have another triangle over here, and maybe it's not oriented the same way, but maybe they kind of look like they're the same, not the way I just drew it. Let's see if I can draw that a little better. Then we can find ourselves wanting to know, is this triangle up here the same as that triangle down there? So what this axiom is trying to tell us is that if I know side A in this triangle and side B in this triangle, and I know the angle between them, theta. So that's side, angle, side. Then if in the other triangle, I can find that same trio, that same triplet. Like if I can find out, oh, in this triangle over here, this is angle A, just like in the first one. This is angle B, that's the same as in the first one. And the angle between these is also theta. If they have the same side, angle, side, then that means that the triangles are equal triangles, called congruent. So that's what this axiom is telling us. And we'll figure out and see examples of how to use that up in the coming problems. So if two sides and the included angle between those two sides of one triangle are equal to those in another triangle, two sides and the angle between them, then the triangles themselves are completely equal to each other. Even if one's flipped over or oriented the other way, they're the same triangles. We call those congruent triangles. Similarly, if two angles and the side between them, so that's ASA, which stands for angle, side, angle. If two angles and the included side between those for one triangle are the same as in another triangle, then those triangles are congruent. Then those triangles are equal to each other. So using sort of just the same little shape argument that I had here, or I should say a diagram to illustrate this. So if I have a triangle over here and another triangle over here, and they kind of look the same, but I'm wondering, are they exactly the same? If I knew, we'll say theta 1, this angle here, and I knew theta 2, this angle down here, and I knew the side between them, I'll just call it S. If I go over to that other triangle and I can say, oh, this one has theta 1 here, 40 degrees, whatever it is, this angle matches that angle over there. And then when I look up here, this angle theta 2 matches over there, and the side between them is the same length, well, then these are equal triangles, even if they're turned in a different position or flipped over or something like that. So the angle, side, angle axiom says if two angles and the side between them of two triangles match, the triangles are equal. And the SAS congruence says if two sides and the angle between them in two triangles match, then the triangles are equal to each other. They're the same triangles. Then there's one more, and the simplest is if all three sides are the same, then the two triangles are equal. And that's the SSS for side, side, side. If three sides of one triangle are equal to the three sides of the other triangle, the triangles are the same triangle. They're congruent. Triangles are congruent. All right, so they give us these statements of ways that you can compare two triangles to try to determine that the triangles are actually the same triangle, just in a different position or location. So definition, this word oblique triangle, because they use that in their original description of our goals for the chapter, a triangle that is not a right triangle. So I began saying we've solved right triangles before, and now we're going to try to see what we need to do to solve triangles that are not right triangles. And now that we know the word for that is oblique. A triangle that is not a right triangle is called an oblique. So we want to consider now solving oblique triangles. So the measures of the three sides and the three angles of the triangle can be found if at least one side and any two other measures of angles, any two other measures are known, either angles or sides. Any two measures are known. So if I know one side, what might the other two measurements be? It might be that the other two sides are, the other two measures known are two angles. And then I'd have angle, side, angle, and we can talk about how we would be able to do that situation to solve the triangle. If I have one side and the other two measurements known are not both angles, but an angle and a side, then it could be that I have the side and the angle between them, or I had a side and I had another side and an angle next to them. This is side, angle, side, or side, side, angle. So, or the other possibility is that I know a side and the other two things that I know are the other two sides, and then I have side, side, side. So we're going to use these annotations that we started to introduce for the congruence axioms, and we're going to start to talk about these three pieces, angle, side, angle, side, 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 as three things, three measures that we know about a triangle. And we can find out all three sides and all three angles if at least one side and any two other measures are known. You need to know one of the sides. If you just know all three angles, well, there's no way to know what the sides would be. But if you know one of the sides and any two other measures, which would be angle, side, angle, or so basically two angles and one side, angle, side, angle, or possibly angle, angle, side. I should have put that other possibility up here. If you know two angles and a side, then the side is either between the angles or next to the angles. You can solve for the triangle. If you know two sides and one angle, then that would be side, angle, side, or side, side, angle, and you can solve for the rest of the triangle. Or if you know three sides, then you can find the angles in between and therefore know the entire triangle. So these are the sort of three situations we're now going to begin studying to figure out how, if you know at least one side and any two other measures, you can figure out everything about the triangle, namely all three sides and all three angles. So that's the goal we're going to slowly pursue, and we're going to have to look at different methods to do that. All right, so let's see the first thing that they tackle here. Data required for solving oblique triangles. Case one side and two angles. So that's what I was pointing out here. Two angles and one side, that's their case one. Case two sides and one angle. And specifically they say not included between the two sides. So here's their number one, or their case one. Two sides are known, side, side, angle. So this is their number two, their case two. Case three, two sides and the angle included between them, side, angle, side. So this is their number three case. And then case four, three sides are known, SSS. That's number four. So they're breaking these sort of three categories and these different possibilities into these four cases. Case one is the first two possibilities, two angle and a side. Then two sides and an angle is broken into two cases, two and three. And then the side, side, side is case number four. So this box is saying, here's our different cases, and they're breaking them up this way because their strategies that we choose to solve the triangle are based on these possible four situations. So let's see if they begin with case one. Well, note, if we know three angles of a triangle, we cannot find unique side lengths since the angles assure only that the triangles are similar, not congruent. So that's pointing out, as I mentioned earlier, that if you know all three angles, you can't figure out the sides because you could have three angles in a small triangle and you could have the exact same three angles in a similar bigger triangle. So just knowing the angles, there's no way to figure out the sides because really the sides could have all sorts of different possibilities. So we won't be able to solve a triangle if we only know all three angles. But if we know one of the sides and any two other things, we can solve the triangles. All right, so in order to begin learning how to solve the triangles, we're going to introduce this first law called the law of sines. So they give a justification or the derivation for how you come up with the law of sines. And I recommend students look this over, but I don't want to use our Zoom time for that. So I'm going to pass over the slides that show you how they get the law of sines and go directly to what the law of sines is so we can begin to talk about how to use it. So this is about the derivation. How did they get the law of sines? They're continuing to show this derivation. And finally, here it is. This is the law of sines. For any triangle ABC, where those are the labels of the vertices, with sides A, B, and C. So again, when they use this notation, we've done this before, but let's remind ourselves that the big letters will be the corners, the corner points, and therefore you could also refer to the angles in those corners. And the little letters refer to the side length opposite that corner. So side A would be opposite angle A, side B would be opposite angle B, and side C would be opposite angle C. So for any triangle like this, with sides little a, little b, little c, and corners or angles A, B, C, if you make a fraction of the side length divided by the sine of the opposite angle, that comes out the same for all three sides and their corresponding angles. Side A divided by sine of angle A is the same as side B divided by sine of angle B, which is also the same as side C divided by angle C. A over sine A equals B over sine B equals C over sine C. This is the law of sines. So what does this do for us? How does this help us figure out things? Well, that means that if in any of these equal fractions, the A is equal to the B is equal to the C fractions, if in any of those pairs, like let's say I just look at the A and the B, if you look at these two compared fractions, then there's four unknowns there: sides A and B and sine of angles A and B if I don't know what the angles are. That means if you know three of those four, you can solve for the one that you don't know. You can make a little equation. There's four things we don't know: two sides and two angles. If we know three of those four, like two of the angles and one of those sides, then we can solve for the missing one. So if I know side A, and angle B, I can solve for side B. And once I can do that, if I know both the angles, I can then solve for the C parts as well. And this will be the idea of how we solve these triangles, using this law to solve for the parts we don't know. And what do we need? We need three of the parts. All right, so that's the law, and let's see if we can put it into action. So it says applying the law of sines here. So let's look at the description of the situation of the problem and then how they go about it. Solve triangle ABC if angle A is 32 degrees, angle C is 81.8 degrees, and side A is 42.9 centimeters. So first, let's take note of what they gave us. So they gave us two angles and a side. And we can make this diagram here. They've already filled out everything. But in particular, they gave us angle A, angle B, and side A. And notice that the side A is not the side between angles A and B. Side C is between angles A and B. So if I knew C, I would know angle, side, angle. But I know angle, and I know another angle, and then I know the side beside both of those. So this is an example where we know angle, angle, side. So using the organizational letters from above. So all the way back before the derivations, sorry about that. We are in this situation. Side, angle, angle, or angle, angle, side, where the side that we know is not between the two angles that we know. So we're working on a case one example here. All right, so they put into the triangle what we know. We know the 32-degree angle, we know the 81.8-degree angle, and we know this side A, the opposite the 32-degree angle.
Did they label it wrong?
Did they? Let's see. I didn't even look here. Let's see.
I think they mean B equals 81 because that's what they label on the triangle.
Yeah, absolutely right. Thanks for pointing that out. I didn't even get to that level. So they put in here that C is 81.8 degrees, and then they put that over here where the B is. So that's interesting. So I need to sort of see what they did here. They're putting sine A over 32, and they're doing B over 82. So it looks like in the work, they're being consistent with the picture. So I think the easiest thing is to fix the original statement of the problem and make that a B. And then everything should match. Then the picture should be correct and the work that they do should be correct. So thanks for pointing that out. As usual, these slides do have the potential for errors in them. Okay, so now it matches the data given matches with the picture. And so what they're showing here is how we can use the law of sines to find missing parts of the triangle. And the immediate way to do it is to say, all right, well, in the information they gave us information about A and B. They gave us the angle and the side of A, and they gave us the angle for B. So we're going to use the two that relate A and B. And then we will know 3 of these 4 things. So we're going to choose of these 3 corresponding fractions, these 3 ratios, we're going to choose the 2 that involve A and B here, because all the information they gave us was about A and B. And they gave us 3 of those 4 things. So then we plug in the 3 that we know. So we know side A, so they put in 42.9. We know angle A, so we put that into the sine, that's sine of 32 degrees. And then they also gave us angle B, which we plug into the sine. And so the only one we don't know is the side B. And so we can solve this little problem for that value, which they did here. So to do that, I would multiply both sides by the sine of 81.8. So then you would multiply both sides by the sine of 81.8 degrees. And of course, we can punch these on a calculator to get actual values. Then these would cancel. And then you would get what they have here, that B is equal to that fraction. And then if you type it all on a calculator, you can get the value of B. So we are solving the triangle, and we just found out this other piece over here. And now we know that this is 80.1 centimeters. So now we know all the A's, the angle and the side, and all the B's, the angle and the side. So I assume they do it on the next slide, but while we're here, what would come next? Well, you know that all 3 angles in a triangle add up to 180. So if you know 2 of the angles, you can figure out the missing angle. So angle C here is going to be equal to 180 for the whole triangle, minus the 2 angles we know, 32 and 81.8. If I subtract off the 2 angles we know from 180, what's left over is the angle measurement from C. And then if I know angle C, I can then use maybe the B's and the C's or the A's and the C's. Once I know angle C here, I can then find out side C the same way that we just found out side B. So let's see if they do that on the next slide. Yeah. So on the next slide, what they're showing is, okay, well, now that we figured out side B, we know that is, what was that, 80.1, was it? Yeah, 80.1 centimeters. We want to find out angle C and side C. So since the 3 angles add up to 180, and the only one we don't know is C, if we solve that for C, as I just did, then you can get the value of C by subtracting the other 2 angles from 180, and then they came up with this 66.2 degrees. Now we know all 3 angles, we know side lengths A and B, we just need to figure out the last one, C. So then we use the law of cosines again, relating 2 fractions, this time making the C the one of the fractions, because we're trying to figure out side C. And then we could use either of the other 2. Now I think they'll probably make a recommendation where when you are solving for the final side, instead of using B, where we figured out B with a calculation, which we then rounded off, use the ones that were given in the problem originally, which was the side and the angle for A. Use these 2 because both of those were given. So set up your law of sines with the C side that we need to find out with the A side that we were given before, instead of with the B side, which we calculated, because then we're potentially having rounding errors in our calculation, and then we use that in a further calculation that can compound the rounding error. So you're better off using all the given information when solving for the missing sides. So I think for that reason, that's why they chose to use the A sides and the C sides in the law of sines. And then in the same situation, we now know 3 of these 4. So you plug in the 3 that we know, solve for the one that we don't know, and that gives you the final value to solve the triangle. Oh yeah, here it is. I thought I had seen this. So here's their caution. Whenever possible, use the given values in solving triangles rather than values obtained in intermediate steps to avoid possible rounding errors. So that's what I was just describing. In the intermediate step, we found B in the step above, but instead of using B to solve for C, use the sides that the information given in the problem, which would mean use the A with the C. So that's what their warning is about here. So this was a complete example 1 of how we were given 3 information bits about the triangle, namely an angle and a side, and we use those to solve the entire triangle. So the process we just used will work anytime you have an angle side. 2 angles and a side that's not between them, you just do what we just did here. Now let's say instead that the side we're given is between the 2 angles. How would that affect things? How would that change things? And so to see an example of the angle side angle situation, they're actually going to do a little word problem here, but they're showing us the triangles. So we can kind of see that we do know 2 angles and the side between them. So let's take a look at the statement of the problem. It says an engineer wishes to measure the distance across a river. So in this picture, the distance across a river will be this length here from B to C. That's the distance across the river. The engineer determines that C, the angle from this point on one side to some point over here, A, that angle C is an angle measurement, 112.9 degrees, and that the angle A between from C to A to B is 31.10 degrees, and the distance between A and C, which they could just walk because you're not having to go across the river, you could just walk that distance, and that distance is 347.6 feet. So from those 3 measurements, 2 angles and 1 side length that's between the angles, we want to find the distance across the river. And as we can see in this triangle that's formed, that would be side length A of that triangle. Okay, so the whole idea here is that you can form a triangle in which you can find out these 3 parts of the triangle, 2 angles and the side between them, by simply measuring them. You can measure the angles. So notice when you're standing here on the shore and you're looking over at this other point on the other side of the shore, you can then just move over to this point A, which just is whatever's convenient, and you can measure the angle between B and A when you're standing at C, and the angle between B and C when you're standing at A. You can use just an angle measurement to do that. And then you can walk the distance from A to C and measure that side length of this triangle that you're forming. And from those 3 bits of information, we can figure out the length across the river, even though we can't traverse that ourselves because we don't want to drown. All right, so what does the process look like? Well, it's still going to use the law of sines. Now, in the law of sines, we normally have A over sine A, B over sine B, and C over sine C. And what we want to do is to be able to compare 2 of these fractions where we know 3 of the 4 things in them. So let's take a look at what we're given here. We are given angle A. So that would mean we could figure out sine of angle A. That's given. We are given angle C. So that means we could plug that in and find the sine of angle C. That's given. And we are given side length B. So when we're trying to use the law of sines, we want to be able to grab two of these fractions and know 3 out of the 4 parts in them. But our problem here is if I grab any 2 fractions like the A and the B fraction or the B and the C fraction or the A and the C fraction, if I grab any pair of those, I only know 2 of the 4 parts. So we need some more information. However, as we saw in the earlier example, if you're given 2 angles in a triangle, you can find out that other angle. So in this case, we can find out angle B by simply subtracting the other 2 angles from 180. Then if I know angle B, I'll know the bottom of the B fraction as well as the top. Then I can make a pair of these fractions in an equation, and I know 3 of the 4 parts. So unlike the problem we just did, where we were immediately given 3 of the 4 parts of the A and the B sides and angles for the law of sines, we were given angle A, side A, and angle B. So that was 3 of these 4. When you have side angles, when you have angle, side, angle, as we did in this case, you first have to get that 3rd angle before you can use the law of sines to solve for missing parts. So that's what they're going to do here. So notice at the very bottom of this slide, they say first find the measure of angle B. And I just tried to explain why you would know to do that, because they just do that and it's harder to memorize these things than to realize why they did it. They first find angle B because then we can use law of sines and have 3 of the 4 parts we need when using law of sines. And they got 36 degrees. So once they got that this was 36 degrees over here, then you can solve for side A using the law of sines on the A's and the B fractions. And then you can solve for side C by using the law of sines on the B and the C fractions, which I assume that's what they do here. So they set up the 2 fractions from the law of sines with A and B in them. We know side B, and angle A, those 3 of the 4, leaving only side A unknown. We plug in the parts we know, we solve for A, and we get the value for side B. I'm sorry, for side A. Then, using the recommendation they made before, we're going to avoid this thing that we just calculated, and we're going to use B and C on the next slide. Well, they didn't even do it. They said, okay, we can do the rest. Use the law of sines to find the length of side A, and then they would do the same thing for side C, which was not given, and they just didn't show that. So then we would do that B over sine B is equal to C over sine C, which means that 347.6 over sine of 36 degrees is equal to C over the sine of, what was C? 112.9. 112.9 degrees. And then we would solve this for C, getting this product divided by that number, and then we would get what C is approximately equal to. So using the same process, it looks just like this, but you would still need to do that for sine C. Then you would know side C, you would know side C, you would know side B, you will know side A, which we just got, and you know all 3 angles. You've then solved the triangle. So there's one more step that they didn't illustrate here. You would want to go back and solve for side C as well. Okay. So we've now looked at examples for case 1, which was where we had 2 angles and a side, and we looked at when the side was between the angles, and we also looked at when the side was outside of the angles, and that was case 1. So they have another one here for angle, side, angle, where the side is between the 2 angles, and they set up another problem. And so this is an example where we have 2 ranger stations, and they have them sort of on a flat line between them. They're saying that these are on a east-west line. That's not a good color for that. Which is this idea that if you're looking north, south, east, west, here's the east-west line. It's this bottom line between them. And then they talk about the angle measurement to get to some fire. So they both see a fire and they spot the angle that they have to look at to see the fire. And that allows them to create a triangle. And they're measuring the angles in each case as how far you are away from the north. So north 42 degrees east is a way of describing this angle here, meaning you start north and you turn toward the east 42 degrees, and then you're looking at the fire. So that's called a bearing of north 42 degrees east. And then from the western station, or the other station, that was from the western station, and then from the other station, it's north 15 degrees east. So in this case, this angle here is 15 degrees, which they kind of stuck a little stick at it. So north 15 degrees east, that's this little angle sitting in there. So the question is, from those measurements, could we find out angle A and angle B? And then we would solve the angle side angle triangle the way we just did in the earlier example. So in this case, we'd have to see that angle A plus 42 degrees makes a right angle between east and north. And so that means if it's 42 degrees up top, that there's another 48 degrees for angle A. So they do that in the first part. Then if we see down here for angle B is the 90 degrees between west and north, plus the extra 15 degrees from north to east. So that means that is going to be 90 plus 15. So all of angle B would be 105 degrees. And they do that next in the diagram. And then lastly, once we know those two internal angles in the triangle, we can find out angle C because they add up to 180. So angle C is 180 minus those other two. And then we find angle C. So that way we sort of use the method of angle side angle here, where you first get the third angle in the triangle. And in this case, we had to do a little work to get the first two as well from these bearing measurements that we were given. But once we know all three angles, then we use the law of sines from B to C and then from B to A to find the missing sides. And that solves the triangle. Now, the way they describe that is to the nearest 10 miles, how far is the fire from the western station? So specifically, they just wanted side length B. So that's all we needed. We didn't need to solve the whole triangle in this problem. But we would then put side B with two of the ones that we know. Since we were told side C, we would do those. And then we could solve for side B as the problem required. Now, we could also go back over here and solve for side A if they had asked for the distance between the eastern tower and the fire, but they didn't. They just asked for the distance between the western tower and the fire. So this is a second example that's a little bit more involved because we have to use these bearing measurements to figure out the two angle side angle angles in the triangle setup. But once that's done, you can follow the exact same procedure to solve for any parts that you don't know. And in this case, they asked for one of the sides we didn't know. Again, feel free to rewatch this video or to look back through these slides because you can pull up the slides yourself off of my stat lab if you want to spend more time and go through these in more detail. And there's only one other thing. So they're only going to study of the different cases we introduced for solving all triangles. In the first section, we're only going to look at the first case. And then the last thing we're going to look at is with the side angle side of a triangle, you can get the area of that triangle. So in the past, you may recall, we've had a formula for the area of a triangle, but the area of a triangle involved knowing a base and a height of a triangle. And so in the derivation for some of their axioms that had up there, we can recognize that the height can be calculated by looking at the sine of an angle. And there's sort of three different ways to do it. So they use that when you have the height of a triangle, the area is equal to 1/2 times the base times the height. This is a goal. This is a formula that we've had from past, usually back into early geometry or algebra, that they just give it to you. But actually, we're going to come up with what's related to that now in trigonometry, where actually you just need any two sides and the angle between them. So let's look at how they show us this. The area of a triangle where you have two sides, notice side, angle, side, and the angle between them, is you take 1/2 and you take the product of the two sides and multiply by the sine of the angle between them. So it's not necessarily the base and the height, but just in this first example, the two sides we know are B and C. So if you know B and C, putting up some A, and this is still B, if you know B and C, then the angle between them will be angle A. And if you take the product of B and C and the sine of angle A and multiply by 1/2, kind of like this formula here, that's the area of the triangle. Now let's say instead that you know sides A and B. Well, if I know side A and B, the angle between those will be angle C. And if I take that same product of the two sides and the sine of the angle between them, I get the area. And the same thing if you know sides angle of A and C and angle B between them. So if you know any two sides of any triangle and the angle between them, you can get the area by doing the 1/2 base times height formula. But instead, since one of the sides might not be the base nor the height, you do 1/2 side times side and you multiply by the side of the sine of the angle between them. So this gives us a nice formula for the area of any triangle. So the note is, if the included angle measurement is 90 degrees, its sine is 1, and the formula becomes area equals 1/2 base times height. Why are they making a note of this? Because this is the formula we had before for the when you have a right triangle, for example. So if this is a right angle, let's say that that was angle A, and we have B, and we have C. Well, if we know the angle between two sides is a right angle, and we know those two sides, like C and B in this case, well, then what you'll see is that C is the base and B is the height of the right triangle. So this ends up being base times height times 1/2 when you have that situation. Okay. Anyway, so nonetheless, it works even when you have right triangles as when you don't. And we're typically going to look at examples where we don't. So here it says, find the area of this triangle. It's not a right triangle. And they give us two sides, C and A, and angle B that's between them. So the formula says I would take the product of those two sides times 1/2 and multiply by the sine of the angle between them. So that's the formula appropriate to this particular triangle. And you don't even really need to label the A, the B, and the C. If you know you have two sides and the angle between them, just multiply the two sides and the sine of the angle between them to get the answer with the 1/2. So they plug those in and they multiplied and they get the area of the triangle. Now notice, keep in mind, area is in square units compared to the units for the measurement of the sides. The side length is a one-dimensional unit and the area of a triangle is a two-dimensional unit. So if you're measuring your sides with feet, then the area would be in square feet. And so they've designated that correctly with their formula result here. Okay, so let's look at this next example. Finding the area of a triangle where instead of the sides and the angles between them immediately given, they give you two angles and only one of the sides. Well, we're not given what the formula requires, so we can't immediately plug into the formula. But as we were just looking, this is an example where we can solve for the entire triangle if we want. We can solve the whole triangle. So even though the formula for the area of a triangle is set up for side angle side, if we were given angle side angle, oops, there we go. If we're given angle side angle, we can get other sides and have side angle side to use the formula, because we can solve the whole darn triangle, as we've already looked at. So it says before the area formula can be used, we must find either A or C. Because if we find length A or length C, then we will have two sides and the angle between them. So like when you're solving the angle side angle triangle, they start by figuring out angle B by subtracting the 2 we know from 180. So they got that this is 102 degrees and 40 minutes. I'll just put that up here. And so then when we know that, we can find A or B by using the law of sines. So in this case, since we know side B and angle B, they're going to find sine A, side length A, by using the A and the B fractions from the law of sines, putting in the 3 that we know to find the one that we don't know, solving for the one that we don't know. And now that they've found A, we know B, and we know the angle between them. So we can do the side angle side formula for the area. So that's what they do this. Now to find the area, we multiply the two sides that we now know by 1/2 and the sine of the angle between them. And that gave us the area. Notice the square centimeters versus the measurement of centimeters of the side length. So even if you have two angles in a side, you can get the area of the triangle. If you have a side angle side, you can get the area of the triangle. All right, so sometimes when you're looking at these problems, the steps that they're doing are not too complicated. The real thing is, how did they know to do that? So you really want, I'm trying to explore why they were motivated to do what they did. So then we can see that they did it. Watching what they did is not as hard as knowing how did they know to do that. And if you're just staring at a naked problem without any description as to how to go about getting the answer, you have to come up with that motivation yourself. So I think therein lies the real challenge that I'm trying to help with here. And that's it. And we have a blank slide at the end.